This is question 2 from the triangle of forces tutorial sheet. And in this question, we're doing something slightly different than we did in question 1 from the sheet. In question 1, we were given the values for 2 forces that were acting and asked to find the third. In this question, we've been asked to do something different, as I said. We've been given the value of 1 force and asked to find 2 of the others. And this might not seem like it can be done easily because we needed 2 forces last time to find the third one, but actually what we can do here is quite clever. We can use a property of our triangle of forces in order to identify not just one, but both of the unknown forces. So what's happening in this question is that we've got a crane and it's got a load or a lift hanging off it, and that has a downward weight of 1200 newtons. And the 2 members that join together, where the winch is for the crane, have an unknown force acting in them. Now, we can presume that the force is are coming together to completely balance out the weight of the lift, because this is a static equilibrium problem, which means our triangle of forces will be a complete triangle that works round starting and finishing at the same point. So with that being said, let's start to think about how we can tackle the problem. Well, the very first couple of steps are exactly the same as we tackle on any problem. The first thing is we know we're going to be using a graphical method, so that means establishing a scale for our problem. Now, there's no one right answer to use for this. There's a limited number of choices you can make. So we can't have obviously 1 centimetre to 1 newton, or your piece of paper is going to be a kilometre long. So we're going to say here that 1 centimetre, again that's our like 1 centimetre line, we'll make it equal to 100 newtons and see how we get on there. That means that to begin with, our downward vector, or downward force due to the weight, will have to be a 12 centimetre line. And that seems reasonable. We'd fit that in a piece of paper. We could maybe even get 1 centimetre to 50 newtons, but it's entirely up to yourself and what piece of paper you're working on. But for A4, we'll try and keep it within the bounds of that. And we can start off by drawing that line. So we know we have a vector pointing down the way. We've got this force that's due to weight. It's acting downwards. So we can draw a perfectly straight vertical line, and we can make it 12 centimetres long. And that's going to be our starting point. That's my best attempt at a line of 12 of these intervals long. I'm saying are equivalent to centimetre in your piece of paper. That's what arrow showing the direction. That's 1200 newtons. Now, what we've got here is a little bit of a challenge on 2 fronts. We've got 2 other forces to add on, but we don't know how big they are, and we don't know what direction they're heading in. But we do know that whatever way we choose them round, they must make up a triangle with this line we've drawn in here. So what we can choose to do is draw in 1 force connecting to the start of the vector and 1 force connecting to the end of it, and then extending those lines out until they meet, and that will form our triangle. But I feel this is a problem that is more easily explained visually than verbally. So let me start off by showing what I mean. Let's say, for example, and maybe I'll indicate these with a bit of colour. Let's say we make this line here, we represent this one in blue, and we'll represent the other one with red, just so that we can see which one I mean. So the blue line, let's say we'd chosen to make that our next vector, adding on to the end of the one that we're joining on to. Well, we know that it has to act up at an angle of 30 degrees from the horizontal. Whether that line is running up and to the right and down and to the left, it will make an angle of 30 degrees if it passes this horizontal line here. So as we've done in previous questions, we'll mark a little dotted line here. And I want to measure up, again, you'd use a protractor for this, an angle of 30 degrees. Oh, I need to be careful, it's not an angle of 30 degrees from the horizontal. And then we did a very silly mistake there. If you look carefully, it's an angle of 30 degrees from the vertical line. So I can still use the line I've drawn. I just need to remind myself that this angle will be 60 degrees because that makes up a right angle. So we'll measure up 60 from here. And the mistake I nearly made is a very common one to make. You would not lose all marks for doing so, but it is a way to start to let a question go wrong. So we know that this has to make an angle of 60 degrees. We don't know if it's going up the way or down the way. So I'm going to move the page slightly to give us a bit more room here. One of the advantages of the whiteboard. I'm just going to extend the line off in both directions because it could be coming down this way, it could be going up that way. We're not sure how big it is yet. We'll find that out in a second. So we know that has to be the case. We also know that from wherever we draw this, the other line will have to connect on to the other end of our vector. So which means this end of the line here, and this line is acting at an angle of 30 degrees above the horizontal because it's 60 degrees from the wall. I'll indicate that in both the diagram and here. So I'll draw the dotted line across here so we can measure from here. I'll show you in the diagram. And of course, there's nothing to stop you measuring 60 degrees round from the vertical line, but sometimes it's easier to measure up from the horizontal. So this angle here must be 30 to make a right angle. So I'll measure up 30 using this special ruler that we have on the whiteboard. And again, I'll draw a red line in here. Now it looks as though we need to extend our blue line up the way for these to meet, and that's absolutely fine. We can just reset our direction to 60 and line it up with this blue line here. And draw up until these two meet. And that's how we solve a problem where we have two unknown vectors. We just connect one to either end of the one vector we do know and then extend them until they meet. So I would always advise doing this in pencil because then you can erase any extra bits you don't need. I'll just be careful not to measure any overhanging bits. As for what direction these two are pointing in, well, remember in any of our triangles, we have to follow a path from start to finish. So if we're coming down the black line to the bottom of the blue line, it means we have to head up here. And then we get to the top of the red line and we come back here. So we follow a path round to the beginning. It means that the combination of all these three forces has no overall net effect. I'm marking these angles I drew as well just to show what they correspond to. Now in this question, we're asked to give the size and direction of the forces. Now the direction, we don't need to say anything about the angles. The angles are given in the question. It does want to know if they're pointing up the way or down the way. So we've answered that question already. We knew what angle they were pointing at. We just didn't know if they were pointing up or down. So we know the blue line, the line that's 30 degrees from the wall or 60 degrees from the horizontal points up and to the right, and the other vector, which we made red, points down and to the left. So the other thing we have to do is to find the size of these forces, and we do this by measuring each line and then using our scale to see how big it is in terms of newtons. So I'll do my best to get a reasonably good approximation here. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20.5. I'll say 20.7 centimeters. And again, if you're doing this on paper, I'm sure you can get a better read than me. But so if we're saying that's 20.7 centimeters, well, that means if it's 100 newtons, this will be 2070 newtons. And that's about the level of accuracy we can get to, is to a millimetre to a tenth of a centimetre. And measuring the red line, well, let me get my ruler lined up with that. Two, 4, 6, 8, 10. I make that just shy of 12, so I'll say 11.9 centimetres. And that's equal to 1,190 newtons. So, and in all probability, that line's probably 1,200 newtons. It looks like this might be intended to be an isosceles triangle, so the red and black line are the same length. You could work that out if you really wanted to by calculation, but we're not required to do that here. And answers within this range are close enough. In terms of an assessment, as long as you have made a good effort to draw the angles and measure the length accurately, a degree of inaccuracy is permitted within the marking scheme. And that's how we solve question 2 from the tutorial sheet for the triangle of forces questions.